So we can start. Good afternoon, everyone. Welcome. So today we have two presentations, and it's my pleasure to introduce the first speaker, Ankur Shiludar. He is a PhD student with Professor Luca. We've been working together on many projects related to modeling, simulation, optimization for the electric power trains. And today, Ankur is presenting on his work on digital twin of electric bus. So I hope you enjoy the presentation.
Thank you, Manfredi, for the introduction, and welcome everyone for the seminar on the digital twin development of battery electric transit buses, and analyzing and simulating energy consumption in real driving conditions. It's a mouthful, but yeah. This is a work that I am doing with a team of researchers here at CAR under the guidance of Dr. Giorgio Rizzoni in a FTA-funded project at CAR. I hope everyone here has seen the Quota 31 bus that has been electric for a few years now. I feel nice to see that bus, to see that the electric vehicles is not just a thing of passenger vehicles, but now it is getting in the commercial vehicle industry as well, and particularly here the transit buses. Although it have been coming in the commercial transit agencies, but there are many challenges that are still these vehicles face in their operation. The biggest challenge they have is the battery lifespan issue. The same battery pack in a bus, depending on how and where it is operated, can have very different battery life experience. There are very limited testing practices and that do not that fails to simulate what happens in the real world in terms of battery life. This lack of information and lack of feedback is determined for transit agencies, and they have been avoiding using these electric buses in their operations until now. Also, with now the buses are there, but if there is a failure, that can be a huge issue. These battery packs in these buses are roughly estimated to be around 25 to 35% of the total vehicle price, and having a breakdown due to battery degrading much faster can be a significant cost and result in a higher maintenance cost of these buses. To help these transit agencies, the goal of this project that we are working here at CAR is to develop a software tool that can be utilized by these transit agencies to understand how the battery ages due to their operations, provide them a way of doing predictive maintenance. To do that, we are using machine learning based state of health estimation algorithms and estimate the remaining useful life. Oh, sorry, my bad. Is it screen 2 or screen 1? No, not this.
And can we double check that the audio is working?
Is it? Have you joined the meeting?
So nice to meet you.
Okay.
I'm not sure about the audio, but it seems like it was working.
Okay. Yeah. Okay. I'm very sorry for that. Okay. Yeah, there wasn't a lot that is missed. Just a figure of bus there and the challenges. But yeah. So with this tool that we are envisioning, that this can help these fleet operators to optimize their operations and also make them feel confident about electric buses to make their buses transit fleets not just have small few buses, but the whole fleet electric in the future. As a part of this work, we are developing a digital twin of transit bus operations in our work. This with this digital twin, we want to analyze how battery degradation happens when the transit buses would be used in operations. This To do this, we are taking into account the actual buses operations. That includes how these buses are driven, what's their schedules, what's their parking, when they're parked, when they're charged, which routes they travel upon, which weather conditions, what are the weather conditions in which they are used, and finally, we are developing a high fidelity digital twin of these buses, including the powertrain, the batteries, the aging models, and including also the driver behavior, because that has a significant impact on the energy consumption and aging of the battery. This this is the main focus of this presentation on how this digital twin of the transit buses performs. This uh, digital twin is developed in a Simulink virtual environment. Firstly, we gather the route and weather information of these transit buses. The route information consists of the route speed limits, the road grade, the bus stops, the traffic lights, all the traffic location from the open source applications such as OpenStreetMaps or Open Topography. We also get the weather information from W Underground. As an example, I've shown the route information for a particular route. Next, we develop a detailed road load model. I guess a lot of you must be taking Dr. Zoni course this year, and you will be learning. You may or may not have learned about the road load model, but in a vehicle uh, in, there are four resistive forces that a vehicle needs to overcome. These are aerodynamic drag, rolling resistance, inertial, and grade, and the torque that should be provided to wheels by produces the traction force to overcome these. In our case, rolling resistance is a big factor which we have modeled with a very complex rolling resistance model for the heavy duty truck, heavy duty vehicles, and integrates the tire thermodynamics as well into it. Using the route information, we want to simulate what the realistic driving of these in the simulator. So we have used a modified enhanced driver model, which mimics a real bus operators driving behavior. Finally, there is a detailed powertrain system, which is a uh, hybrid powertrain simulator consisting of uh, equivalent circuit model and a thermal model of lithium-ion battery pack with the aging, which will be incorporated later on. In addition to the road load, there is auxiliary power usage, which is also quite important to be characterized. And for that, we are using a duty cycle based modeling approach, where where major auxiliaries like the HVAC and the battery thermal management system are modeled as temperature dependent loads. Before I go into how the simulator performs, let me just give you an idea of uh, how we are going to do the model validation. And for that, we use the data that Kota graciously provided us of the real world data that Kota provided us of their fleet. Kota has New Flyer XC40 buses in their fleets. They have been using these buses for a few years now. On the plot on the right, I have it shows how much mileage these buses have covered. Collectively, the data that Kota has provided consists of 25 buses, which have covered around 4,500 trips the in the last 4 years. The data we have is trip aggregated, and we will be using this aggregated data for validation of our models, of a web digital twin model. Now, I told you like we have all these sources from where we're getting the real world inputs for a web digital twin. I'm taking an example of Kota Route 31. It shows all the bus stops where which bus stops are taken. We can in our simulator we are able to simulate any particular day to understand what would be the energy consumption. I'll take an example of today. If the bus would have been driven at 11 a.m. this morning, the temperature was around 22 degrees Celsius on average at 11 a.m. Furthermore, the driver aggressiveness can be chosen as calm, normal, and aggressive. Here it is, for this example, I'm assuming a normal driver aggressiveness driver. The outputs are the vehicle speed, in which you can see that the vehicle performs like a realistic vehicle, we would assume. It stops at all the traffic lights, at the bus stops. Even at the bus stops, we are including the variation in the passenger count. This is done so to mimic real life, the real life. Right now, this is randomly assigned, but we are working on getting the actual passenger count from quota as well. So in future, this will be replaced by that work. For this Route 31, the bus on the bottom, I have shown the signals from the battery. For this route, the energy to battery SOC is depleted by roughly 5% to do one trip on this route. The battery current is between minus 200 to 200, and the temperatures and voltage are shown. With this, we can perform the energy analysis. For this is for this example. We see that from the Sankey diagram that most of the energy that isn't stored in the battery is sent to the wheels, which makes these buses highly efficient, around which roughly 80% of energy is being used for propulsion. Furthermore, not just this, with the regenerative energy that the braking that is there, roughly 50% of the energy that is required for the propulsion comes from regenerative braking. This is with simplistic models, but from the data that we have observed, there is possibility of further improving this, and a work is being done to capture that trend in our models as well. Right now, it is around 50% for this example, though. The auxiliaries in this case are not that much in power consumption. They don't consume a lot of energy because it was a relatively uh, nice day out today. It wasn't too cold or hot. Now to do the simulator validation, what we did was we collected data for weather data for these for 1 year and simulated thousands of trips on using this simulator on Ohio supercomputer. We varied the days so that varied temperature and also varied different driver behavior. Here I am showing how the results from the web simulator match with the real world data that Coda provided us. In the red are the experimental data, that is the trip aggregate data from Coda, and in blue is the are the results that we get from our simulation. On the left, it is the auxiliary power consumption as a function of average out ambient temperature, while on the right, it is the energy consumption. We see that our model is able to accurately capture the trend in what is observed in the real world with very high accuracy. And this also shows the capability of our simulator to mimic the real world in simulation, which is something that we started with. Finally, we now start looking into case studies. First was to understand what is the influence of seasonal weather variation on energy consumption. Depending on the route and the weather in a month, the energy consumption can vary by a lot. In this case, it can vary by plus minus 40% in case of buses that are operated at quota, and that the results that we got, these variations are that we obtained from experiment are also similarly obtained in our simulations too. Furthermore, we are also able to characterize how much energy each auxiliary component is consuming. As I told earlier, that two of the biggest auxiliary power source components are the EHVAC and the BTMS. For the relatively mild temperature conditions in the spring, summer, and autumn, EHVAC is still one of the biggest energy consumption among all the auxiliaries. But in winter, along with HVAC, BTMS for heating the battery takes in a lot of energy from the battery, and can account for roughly, both of them account in total can account for 80% of the auxiliary power consumption in these battery electric buses. At the end, we also did what is the impact of driver aggressiveness on the energy consumption. To do this study, we randomly selected eight routes from the quota and varied the driver aggressiveness between calm, normal, and aggressive. By varying the driver aggressiveness, the travel time changes marginally, but the impact is observed the most on the energy consumption. Driver, like on the right, I have shown 4 of those routes, the energy consumption or variation on 4 of these routes when we change the driver aggressiveness. Driving in an aggressive manner results in roughly 8% more energy consumption compared to a normal, while driving calmly can reduce the energy consumption by more than 30%. Which is really drastic, which is a drastic difference between due to just changing the driver aggressiveness behavior. Finally, with that, I come to the end of this work. We developed a high fidelity digital twin of these BEVs, which incorporated detailed road load models, powertrain model, lithium-ion battery model, and with this, we were able to capture the influence of ambient conditions, particularly temperature, the differences in routes and driver aggressiveness on auxiliary and BEV energy consumption. We were able to validate our model with the in-operational data that Coda provided to us. We also performed a large-scale simulation study to assess the impact of the weather variation and driver aggressiveness on BEV energy consumption. With this, the next steps that we are working on is to further improve the model, include aging model along with in the battery to understand how the usage of these buses in the day-to-day operations will have an impact on the lifespan of these buses. And as I said, like there is these buses have a large can recuperate a lot of energy to regenerative braking, and is something that needs to be further studied, and we are working on that to improve our models to have better regenerative braking strategy, and refinement of auxiliary component is also underway. Just the references for the work for some of the things that we have used in this seminar. And then I would like to thank Dr. Rizzoni for giving me the opportunity to work on this project sponsored by the US DOT Federal Transit Administration and Quota for providing us with the data for validating our model. I would like to also thank Amy, Luca, and Priyanka who helped me in making this presentation for the seminar. With that, I thank you all for graciously listening to me, and if you have any questions, I would love to answer them.
Thank you, Ankur. And I think we have time for questions, so feel free to raise your hand or type in the chat if you're online.
I do have a question. First of all, thank you. It was an interesting presentation, interesting work. And I was just wondering, you referred at some point to like a tire thermodynamic model. Is it correct?
Yeah, tire thermodynamics model, yes.
So given the fact that you have the route of the buses,
yes.
Considering the diagram that you showed, I assume that you're not including any, you're only considering the longitudinal effects.
Yes.
Right? How come have you chosen to disregard the lateral dynamics since you have the information, if you want like a very accurate model?
So the thing is, lateral dynamics doesn't have impact that much on energy consumption. It is mostly the longitudinal dynamics that have an impact. So that is that is one reason of disregarding lateral dynamics in our work. However, I would point out that we have included the that the impact the lateral dynamics have, because there would be we have the route, so we know where the vehicle has to make a turn, and it cannot make a turn at high speed. So we have included before in the junction the vehicle has to slow down and then accelerate. So these things are usually disregarded, but we have taken it into account since we have that information, and given there's possibility of regenerative braking, how much energy can be generated, taking into account has been highly beneficial for us to get accurate models that match with the real world expectations.
Thanks.
Yeah, sure. Thank you for the question.
Could you go to slide 9?
Sure.
With the between your model and the actual data, do you have any insight as to why it seems like your model does a better job at higher temperatures than temperatures that are below 0?
Yeah.
Do you know why that is?
Yes, this is something we are trying to investigate right now. Our model is well calibrated for, if we look at this picture, for about 15 degrees Celsius, but there's slight deviation at low temperatures. We're trying to understand whether it is coming from auxiliaries. That is why I said we are trying to define our auxiliary component modeling. It can also come from the road load. We might be overestimating the energy consumption. That's why our results are higher than the lower in lower temperatures compared to the experimental data. And just as a last point, I would like to add one more thing. In Columbus, it doesn't get too cold, so we have very few data points in that, and which can be bringing the trend downward. If we are working with other transit agencies to gather more data, and once we have that, we can then recalibrate our models, recheck if the performance is still good when we do it for some other transit agency. Thank you for the question.
We have time for a few more questions. So
I have one last, if you want. There was a slide with the energy consumption divided by season, and I noticed there was yes, this was there is a strong difference between the seasons. So, would you, after all your simulations and all your studies, would you recommend to have different types of buses for each season? Let's say, should Kota change bus type seasonally to save on energy consumption?
I don't think that would be a viable strategy because these buses are expensive, and if you're just going to use the buses in a particular season, in the remaining time these buses would be lying in the park situation, which might be detrimental to their battery because these are battery electric buses. It's not like they will not age. Even when they're sitting, they will have calendar aging going on. So probably not a good idea.
But so do you design for winter and then you just over design
I think that's what the bus manufacturers must be doing right now to be able to, because thermal comfort is a must for the humans that would be in the buses as well as for the battery. So over developing for the worst case scenario is something I think these manufacturers must be doing.
So that this study was intended to identify the worst case scenario, worst condition for energy consumption in this case. And
yes. Also, I don't think we have from the data that we are simulating the worst case yet. There might be situations that if we take into say the buses that are in New York or in Houston, Texas, they have their temperatures go very low to very high. So that is something we should be doing to validate like how our model performs in these extreme conditions.
But still, here is almost 50%, right? 40%.
Yes. So here it is 52. If you look in for the December, it's around 20%. It's around 2 to 3 kilowatt hour per mile, and energy consumption of auxiliaries is around 1.5. So it's 50% of the total energy consumption is just to power these auxiliaries.
Yeah.
That's why it's important to understand how much energy these are consuming and to have detailed model to study that as well. Yeah, thank you.
There's actually one last question online.
Oh.
Ankur.
Oh, sure. I can. We'll have to.
I can read for you. So Professor Sagar is asking, if you're not familiar with the concept of a digital twin, can you explain what's the difference between that and a model?
Okay, so this would, like the work that we are doing would seem like a model, but the consideration of all the aspects that that the bus will experience in real world is something that makes a digital twin. We are not just taking into account, we are not using some regulatory drive cycles. We are simulating the buses on real world routes, transit buses routes that are there. We are considering real world time varying weather conditions that these buses would go through. So all this thing, I believe, makes it a digital twin rather than just a vehicle simulator. Thank you for the question, Professor.
Yes, I think some other comments, so let's read it.
I think Athar has a question.
I think maybe one, yeah.
Thank you for your presentation. Yeah, we did this type of study on school bus fleet.
Okay.
Yeah, recently. And my question is that how are you capturing the door open effect in your model? And
So-
similarly, second thing, how are you capturing the effect of bus wall, the passenger inside the cabin of the bus, and the window effect on your energy consumption?
So in this work, we haven't dwelled in detailed modeling of the HVAC, like what you're saying, like modeling the opening of the doors, which will have an impact on HVAC. Also, like the external conditions, which like heating from outside or the radiation. We have not considered that. We have a very simplistic. We have a simple model. I can show it to you. So we have using an average approach for HVAC, which we obtained from literature that gives how much energy is on average required from this auxiliary component, which is HVAC, and as a function of temperature, and that's what we are using, and it seems to be working well for the work that we have done. But yeah, definitely, it is something worth exploring if you want to further improve the digital twin of this vehicle. Thank you for the question.
Okay. And there are a couple more comments from Professor Martin as well, but it's mostly on the functionality of things, so we have a whole seminar just on but it's important to make sure that we use the correct definition. So
Yeah.
Take a look at the comments.
Sure.
I think we can thank Ankur for the presentation.
Yeah. Oh, I closed the door. Let me open that. Share the screen.
All right, while Luca gets set up, I will introduce the second speaker. So our second speaker today is Luca Meda, who is coming from Milano and has been a visiting scholar here working with Dr. Stalker for a year and a half at this point. Unfortunately, he will be leaving us in the next couple of weeks, so very sad about that. But he worked on projects related to data-driven control and optimization of energy systems, and he will be presenting some of his work here today.
Okay. Thank you all for the introduction, and thank you all for coming to today's seminar. So today I'll be talking about what we did on physics informed machine learning for score compressor modeling, and with Dr. Stocker and Dr. Canova. And this is part of like a larger project that we are doing, a new RP project we are doing with Ford about the development of computational efficient and predictive model for vacuum compression systems. And this is specifically applied to light-duty electric vehicles, and this is useful to support the design and control of advanced thermal management systems. And the idea and the approach that we're taking is that to try to develop hybrid modeling techniques, both to the static and dynamic components in the different systems. And what we want to achieve is like trying to retain the accuracy and exploration abilities that are available to common high fidelity physics-based model, but trying to exploit some of the benefits of the data-driven model to improve the computational efficiency of the predictive model for the vacuum compression system. And this is just a quick overview of the whole system that we are trying to model. And specifically in this presentation, I'm going to focus on the development of a static map for the compressor to predict the isentropic and volumetric efficiency that are necessary then to predict the whole efficient system in the vehicle. What is a scroll compressor? So basic introduction. So scroll is a recent geometry that is used in the automotive industry to using vehicles for economical advantage, of course, but also because they are known for their efficiency and their reliability. This kind of new technology, and the properties that we're interested into from a mathematical perspective to develop our model are that these are fixed displacement compressors, so the volume of gas per unit of time is constant, but they're variable speed, so speed is an input that we need to consider in developing the model. And the objective is, as I mentioned before, is the identification of the volumetric and isentropic efficiency maps. And these are done from sparse data that are usually provided by the compressor supplier to the automotive developer. So why do we need to work and do research on this specific topic? Because again, data are often provided by suppliers, and the data are limited to near optimal range. So we don't have wide data set covering the whole range of operation of the compressor, but usually only limited experiments run by the supplier to provide a representation of the ability of the component. So all the startup, shutdown, and other conditions that are common when the component is integrated in the vehicle are not represented in the data set that are available to develop models for the specific compressor component. And this happens because experimental testing is costly, it's consuming, and so this is why it's not always available to do more experimental testing and providing more data. And a problem is again that while we're trying to run some simulations, we notice that 30% of the points in the simulation are extrapolating to the trend. So they're outside the boundaries of the range that is tested and then provided in data set by suppliers. So the idea is that the state of the art in this kind of modeling can be divided mainly into big groups: the physics-based and the data-driven models. The physics-based models are usually based on complete thermodynamic equation for the working fluid, and they need the complete definition of the geometric parameters for the component. And since every detail and every step of the compression process is modeled through specific equations, these models are usually known for this low computation time. And they require extensive data that are again about the compressors that are not always available. On the other side, data-driven and black box models can achieve high accuracy in predicting the compressor behavior and performance, but the downside is that the accuracy is subject to the data availability, and we said that's one of the main problems in this kind of setting. And again, there's not like an actual physical guarantee on the model performance when we are extrapolating outside the boundaries of the training dataset. So the objective, like considering this, like the positive and the negatives from these two approaches, is to try to learn the compressor map from space data and extend the models so that it can work well, it can work like be robust also across the full operating range. And we can maintain some sort of interpretability so that we can guarantee on the model performance in extrapolating conditions. And also we can add fast computations is the final goal of the project again. Okay, fast computing models for the whole efficient system. And how we can achieve this goal is to incorporate some domain knowledge and physical constraints in the classic data-driven and black box approaches. And this can improve extrapolation of design regions and can offer greater robustness. And we can try to enable the model to respect some physical limits, even when the data are not available in these specific regions when we want to enforce the physical constraint. The modeling inputs in this for this specific work are two-dimensional parameters. And this choice is made because by choosing dimensional parameters and making sure that the model is more robust to different compressor applications and geometries. So the two inputs are the pressure ratio and the Mach index. So they represent the ratios between the pressure at the exit and at the suction of the compressor, and the Mach index represents ideally the ratio between the tangential speed in the machine and the speed of sound. And these are two parameters that can represent the inputs that we have available at the compressor during the simulation of the refrigerant system. And we want to predict again the volumetric and isotopic efficiency, as I said before. These are like two quantities that represent the volumetric efficiency, the ratio between the actual mass flow rate displayed by the compressor versus the theoretical mass flow rate. And so this is kind of one of the measures that we have to assess that, the performance, the actual performance of the compressor when it's working and applied to inside the whole vehicle and simulation of the whole vehicle and the refrigerant system specifically. The isotopic efficiency instead is assuming like an isotropic process, and so computing at enthalpy, assuming that the refrigerant of the compressor is like we are observing like an isotropic process. So these are two quantities that are important to assess the performance of the compressor, and they're also important in the refrigerant system to then predict some of the main quantities that we need to develop a model for the other heat exchangers. For example, the mass flow rate and the power of the compressor. That are two key quantities that we want to like derive from our model. So the approach that we are taking to integrate the classic data-driven approaches with some kind of more advanced like physical knowledge on the system and some more advanced physical constraints to control the behavior of the system in extrapolated conditions, instead of applying a symbolic regression approach. And for those of you who are not really familiar with the algorithms, like these symbolic regressions encapsulate like different models, in which we are not trying only to identify the best, the optimal parameters, but we also like trying to identify at the same time what is the best model and what is the best parameter. In which sense? In the sense that we are exploring the search space that we are exploring with these algorithms. It's not just a set of coefficients, but we are also exploring a model space that is made of analytical expressions. So we're looking for, in simple terms, we're looking for formulas using operators, starting from the basic addition, subtraction, and whatever, moving to whatever kind of unary and binary operator you can think of based on your inputs. And the idea is the algorithm is a multi-objective optimization algorithm, so we are not only trying to find the optimal expression based on the accuracy, but we are trying to balance the accuracy with the simplicity based on a definition of a complexity metric in the algorithm. And the other interesting features about this approach is that we can integrate constraints in the model structure, for example, in the number of terms, in the complexity of expressions. And the output is easy to export and is easy to interpret, since the output is a closed form expression, so a classic interpretable function formula connecting the input, relating the inputs and the output. So this is just a brief overview. The algorithms that we are implementing in this work is mostly based on the implementation of a genetic algorithm approach to implement symbolic regressions. And so with different steps to identify the optimal function based on, again, accuracy and complexity. And we are trying to implement this approach here to, again, to learn compressor efficiency maps from sparse data. Here, quick animation right from the library that we're using, which is called PySL, which shows a little bit what is the process. So, exploration of different expression, trying to optimize the coefficients at each steps, and then retaining all the optimal functions, and then step by step trying to achieve and obtain the expression that is able to model the data available and doing it in with the lowest amount of terms. Again, trying to contain the complexity of the expression. So I already mentioned some of those, but what are the advantages of this approach? Is that we have more interpretability. The result is a function, so we have full insight on how the efficiency vary across the input space, and we know of course that how the model works in the end outside the supplier data range. So we are sure that the model is not we are not risking the fact of obtaining prediction outside the physical ranges that we expect from a compressor performance. And then we can integrate physical constraints with two different methods, integrating virtual points that represent a known relation of specific conditions in the input space. And this is often one of the downsides in Blackmore methods that often fail in handling constraints or handling prediction in unknown scenarios. And portability. So the idea is to incorporate this model with the old model for the refrigerant system, and so this is easy to embed in any simulation environment, and then eventually in a real-time controller. And the way to incorporate physical constraints is basically done in three steps way. So we start from modifying the loss function, that is the final optimization goal to reach for the algorithm. So we are not only including a classic MSE metric, but we are trying to add different terms to force greater penalization on those candidate functions that are not satisfying the imposed physical constraints. Again, I mentioned we are generating these virtual points, and this is something that usually does not work on common machine learning approach, considering that here we are exploring a different model search space. And we're also reducing this model search space of candidate expression functions by including only a limited set of unary and binary operators that we know from previous works are expected to be observed when modeling efficiency maps in the core compressors. And I won't go into too much details about the single constraints, but the idea, for example, is if we know the behavior that we are expecting from the efficiency maps, a specific limit condition, for example, when the pressure ratio goes to infinity or goes to 1, that are the two limit conditions that we are not actually observing, but represent the two limits, the boundary limits of the input space. We can modify the loss function to include an extra term when we are penalizing this function for which the prediction of the limit is way off compared to the actual known limit that we know from the theoretical study on the behavior of slow compressors. So estimating for each candidate function, we can estimate numerically the limit, and then again adding an extra loss term to penalize those functions for which the prediction of the limit is not coherent with the physical result we expect. And we can do that based on a set of 4 physical considerations that are derived from different theoretical work down slow compressor. And another thing, the same approach can be done with gradients. So if we know generally the behavior that of the efficiency maps when the pressure ratio or the Mach index are increasing or decreasing, we can add an extra penalization terms to penalize the candidate expression that are not satisfying the sign of the gradient in specific range of the input space. In this way, again, we are trying to penalize more the functions that are not showing the behavior that we expect in terms of the derivative compared to one of the two inputs. Okay, so these are the two main. This is the whole algorithm and the way we are integrating constraints in the algorithm. And the idea is trying to train and see how this overall framework can be applied to different compressor geometry conditions. So one of the things we want our model to be successful on is be able to not again overfit a specific data, so to be able to interpolate the data only in a specific small range of operation, but a model that, since it's based on specific physical known constraints, can be applied to different compressor geometries, so different, for example, displacement parameters, different refrigerants, and different speed ranges, so that the model can be easily exported to different kind of compressors without having to retrain or redevelop the whole framework and the whole modeling steps. And as you can see, especially what's noting out the data points available for each compressor that we are testing here is in the range of from 37 to 48. So again, we are not working with thousands of data, so that are common when they are doing machine learning works. But here we're working with a really limited number of data, and so again, so it's important and to develop models that are able to handle the sparsity of data. And another thing we are testing, we are getting models that are experimental, such as compressor 2, but also models that are whose data are provided by supplier sheets. So basically, the supplier of the compressor is giving to the automotive companies, giving the results of the experiments they run without providing any information on how the condition of the experiments, or if they actually experimented all of these 37 data points, or some of them are actually interpolated based on experiment run on adjacent conditions. So we're trying to see how the model performs where data are collected in different ways. And to validate the performance of the model, we are not just doing, let's say, a classic training validation process, in the sense that we are not only splitting the data randomly in training and validation, but what we are interested in is observing the performance of the model when we are training the data only on a subset of the available data that represent the optimal range of conditions, and then see how the model performs when it's applied to, let's say, more or less 20% of the data representing the boundary conditions of the data set. Again, because we want to test a model that in a real scenario can be able to extrapolate from the optimal range and be able to accurately predict also the condition of the compressor in more at the boundary conditions of the operating range. And so here we can see some of the first results on the three compressors. So here you can see the difference between the training points and the validation points. We can see, and the results you can see are different expressions based on the inputs, so simple closed form expressions relating the inputs and the outputs of the compressor. And we can see in this compressor one that is based on supplier sheet data, higher error on the isotropic efficiency, which are slightly lower when we apply the model for compressor 2, which is then made of data collected with experiments. And you can see the slightly lower errors here, and you can see, again, the condition that we are applying to define the validation points. And finally, also the results for compressor 3, where we have another condition for the validation points, and the error again are lower compared to the first compressor, where the data are provided by suppliers' sheets. So there's less control on the actual experiments run by the suppliers before providing the data. An interesting thing that I want to mention, like before ending the presentation, is that okay. So here we have a couple of the different errors, and the performance are like satisfying. We'll generally be able to keep the errors like in the range between like 1 and 5%. Again, we are not trying to find the model that has the best accuracy based on the data available, or models that is possibly able to be robust when we don't have data covering the whole input range. And the way we are trying to validate this is comparing our model, with some common semi-empirical methods that are available in the literature. And what we want to do is like compare the prediction of the mass flow rate, which is one of the key outputs that we can derive from the volumetric efficiency map. And the idea is to see the performance of the three models, our model versus the literature models, when we are using the whole training dataset to train the model. So imagine we have all the data available and see what are the performance of the three models. And then again, what are the performance of the three models when we are removing some of the data at the extreme condition of the dataset, so the boundary condition of the dataset. And it's interesting to notice how, in general, our model compares well. When we are using all the training data already, we are seeing only higher errors for our model when we are training compressor 1 with all the available data. And again, this is interesting, and it's probably also interesting that our model is able to achieve lowest error when we are using compressor with experimental data, so that are more realistic and represent the actual dynamics of the actual physics of the compressor. But the most interesting thing is that when we are training the data, removing some of the training point and then testing on those points to see the performance on unseen scenarios, we can see how some of the classical approach, for some of the classical approach, the errors achieve very high two-digit errors, so 15 over 20% errors. And so we can see how this model can achieve a perfect or really good accuracy when we are training on all the data and where we are actually overfitting basically the data set we have available. But then we can see our model, which is maybe less accurate sometimes, for example, for compressor 1, but when we are removing some of the data, and so we are trying to predict unseen condition, our model can be more stable and more robust and achieve the consistent level of accuracy, while the other models risk of completely losing their predictive power when we are applying those models on different conditions that the ones we have available in the data set. So to conclude the presentation, the idea of this work is to develop an interpretable, physically consistent, and robust model, so that in the end we can obtain static efficiency maps for score compressors. And this is important because then the model is again integrated in the simulation of the whole thermal system for the lightweight electric vehicles. So it's important to obtain physically consistent results, so that then the simulation of the whole system is more robust and more physically consistent if we are trying to develop a data-driven model of the whole refrigerant system. And the model is validated on data with varying geometry, refrigerants, and different collection methods. And we integrated already this model into high fidelity GT models, GT pool models that are used, for example, in our project by Ford. And so we had the possibility of testing our model can improve the extrapolating performance of the compressor in simulation on the high fidelity physics-based model. And this work is part of is actually the main topic of the publication that's now in progress that we are submitting soon. And I want to conclude the presentation by thanking Ford Motor Company, University Research Program for providing support for this work, and specifically Sunil Katagada, Patrick Yuska, and Judy Che that are part of the team that is developing this work on Ford side. So with that, I conclude my presentations, and I'm happy to answer some of your questions. Thank you.
Looks like we have time for a couple of questions.
With a smaller progression, how do you bound your regression so that you end up with a function that is approachable for a solver like GTcool? How do you ensure that it doesn't end up with some crazy discontinuity or something? Is that inherent to the fitting process that converges away from those things, or is that something you have to impose on it?
No, so the idea is since like the idea in the end, after training the model, you obtain an expression like this. So in your input range, you have full control on like what's the behavior of the efficiency maps, because you actually know in the formula you can have the actual prediction. So the idea is like you first you enforce the constraints to like control the general like shape of your functions based on all the knowledge that you have on again gradients, limit conditions, known relations to virtual points, and then once you get your the idea of the way symbolic regression works, you have you don't only have a single optimal output, but you have a set of outputs with the respective score for the accuracy and the complexity. So the idea is that you can try to analyze some of the outputs and compare trying to find the optimal point between accuracy and complexity, but at the same time you can run checks, for example, to be sure that this expression does not like, for example, the efficiency always needs to be between 0 and 1. So you can always control if this expression like satisfy the condition. So then you are sure that when you're simulating the model, you will always observe output that are physically consistent. And then it's simply integrated by in GT model by generating like complete map given input and output conditions starting from this formula. So you generate, for example, I generated, I don't remember, like 90k points based on this formula at each possible conditions for the two inputs, and then integrated that in GTpool so that then GTpool basically have like complete. Basically, we have a full coverage of this expression in GT, and so we are sure that GT has not space for extrapolating because we are providing points for every condition possible, and we know that the expression is physically consistent. So that's the way we are doing it.
I'll ask it. So you mentioned at the beginning that there are some physics-based models.
Mm-hmm.
How similar do the surface plots of the results of those look to the surface plots of your functions that you get?
So the idea is that I cannot. It's not important. The idea is that I cannot apply these physics-based models. And the thing is, like, to apply these physics-based models, you need specific geometric parameters provided by suppliers. These parameters are not available in general, are available only to suppliers and are not made public when the data set are shared. So these physics-based models can only be developed by the suppliers that know or a university research team that has their own compressor and they can know exactly every compressor parameter. And so I cannot generate a map to have a full comparison for this reason. So we are not able to develop these models.
You said that the compressors that you have, like, are they similar or like in performance, or like they're quite different because the maps that you obtain that you completely different for each, or also the equations are quite different from one another. So,
so the idea is like they are different in the way they adapt to the different data, but we observe some. We want to observe some coherent pattern between the different models. So, for example, we always want to observe like this the bell shape, for example, for the isentropic efficiency versus the pressure ratio. And we have it in different ways. Like, for example, in compressor 1, it looks like this, and then here we have the same bell-shaped relations in the isentropic efficiency versus the pressure ratio, again adapted to the data. Because, for example, like the way the location of this maximum for the relation between the isentropic efficiency and the pressure ratio depends on the geometric parameter of the compressor. So each compressor will have the same shape, but will have slightly like different shape based on the specific geometry compressor. So the idea is that the general shape, general limit conditions are the same for each compressor. Then the final output is adapted based on the data that reflects some of the specific geometry of the compressor that are different according to, again, some of the refrigerant that they're using, some of the displacement, and all the other conditions that depend on the specific compressor.
All right. Thank you so much for presenting, Luca.
Thank you.